Chapter 4: Defining Functions. In this chapter we introduce a range of mechanisms for defining functions in Haskell. We start with conditional expressions and guarded equations, then introduce the simple but powerful idea of pattern matching, and conclude with the concepts of lambda expressions and operator sections. 4.1 New from old. Perhaps the most straightforward way to define new functions is simply by combining one or more existing functions. For example, a few library functions that can be defined in this way are shown below. Decide if an integer is even. Even is a function that takes an a, which is an integral, and goes to bool. Even of n is n mod 2 is equal to 0. Split a list at the nth element. Split at takes an int and a list of a's and returns a pair of lists that contain a's. And it's defined as follows. Split at n x's, take n x's, drop n x's. Reciprocation. Recip takes a fractional a recip of n is 1 over n. Note the use of the class constraint in the types of for even and recip above, which make precise the idea that these functions can be applied to numbers of any integral and fractional types, respectively. 4.2 Conditional expressions. Haskell provides a range of different ways to define functions that choose between a number of possible results. The simplest are conditional expressions, which use a logical expression called a condition to choose between two results of the same type. If the condition is true, then the first result is chosen, and if it is false, then the second result is chosen. For example, the library function abs that returns the absolute value of an integer can be defined as follows. Abs goes from ints to ints. Abs n if n is greater than or equal to 0, then n else negative n. Conditional expressions may be nested in the same sense that they can contain other conditional expressions. For example, the library function signum that returns the sign of an integer can be defined as follows. Signum goes from ints to ints, signum n if n is smaller than 0, then negative 1, else if n is 0, then 0 else 1. Signum, okay. Note that unlike in some programming languages, conditional expressions in Haskell must always have an else branch, which avoids the well-known dangling else problem. For example, if else branches were optional, then the expression if true, then if false, then 1 else 2 could return the result 2 or produce an error, depending upon whether the single else branch was assumed to be part of the inner or outer conditional expansion. Guarded equations. An alternative to using conditional expressions, functions can also be defined using guarded equations, in which a sequence of logical expressions called guards is used to choose between a sequence of results of the same type. If the first guard is true, then the first result is chosen. Otherwise, if the second is true, then the second result is chosen, and so on. For example, the library function abs can also be defined using guarded equations as follows. Image. Aha. That's annoying. Okay. The symbol pipe is read as such that, and the guard otherwise is defined in the standard prelude simply by otherwise is true. Ending a sequence of guards with otherwise is not necessary, but provides a convenient way of handling all other cases, as well as avoiding the possibility that none of the guards in the sequence is true, which would otherwise result in an error. The main benefit of guarded equations over conditional expressions is that definitions with multiple guards are easier to read. For example, the library function signum is easier to understand when defined as follows. Okay. So let's, is annoying. Okay, so this doesn't work in the terminal. 4.4, pattern matching. The images, I mean. Pattern matching. Many functions have a simple and intuitive definition using pattern matching, in which a sequence of syntactic expressions called patterns is used to choose between a sequence of results of the same type. If the first pattern is matched, then the first result is chosen. Otherwise, if the second is matched, then the second result is chosen, and so on. For example, the library function not that returns the negation of a logical value can be defined as follows. Not false is true and not true is false. Okay. Okay, so I think I know how to write the guards thing so that we don't need the image. Oh no. So let's call it abs2 of, wait, let's first say abs2 goes from integer I to I. No. Whole. Wait. Oh no. Abs. Oh, okay. Abs just goes from int to int. I wonder why it doesn't just go. Why it doesn't use classes here. Okay. So abs2 of n. N greater than 0. I think is written like that in Haskell. If n is greater than 0, n, and then otherwise? No, I have to look this up. Wait. Guards. I don't think you can see what I'm doing right now, but guards. Oh yeah, so it is the keyword otherwise equals negative n. Oh, how have I set this up? Let's see. abs2 of -5 is in error. Okay. The Windows recording thing is above that. Oh my god. Okay. Okay. So it's saying no instance for num int arising from the use of negative. Huh? Let's try their definition of abs. If n greater than 0, then n else negative n. Oh. Abs. Oh, so it's just, okay, I know what the problem is. I think. This is the problem. No. Okay, now it's a different problem. So right now I'm SSHing into a Linux machine because I don't know how to set up all this stuff on Windows. But the downside is that I use Emacs with key cords. Well, whatever. abs2 of -5, so that does work. So the problem was that I was using the negative function. If I just typed abs2 -5, then it thinks it needs to apply the function minus to the function abs2 and 5, and then it's saying abs2 is not an integer. I think that's what was happening there. And the other error is the fact that abs is already built in, so I can't define it. abs3 -5. Okay, let's move on. Okay, pattern matching. Yatta. Functions with more than one argument can also be defined using pattern can also be defined using I don't know where we were. Oh my God. Why is this so difficult? Okay. Pattern matching. Many functions have a simple and intuitive definition using pattern matching, in which a sequence of syntactic expressions called patterns is used to choose between a sequence of results of the same type. If the first pattern is matched, then the first result is chosen. Otherwise, if the second is matched, then the second result is chosen, and so on. For example, the library function not that returns the negation of a logical value can be defined as follows. Not false is true, not true is false. Functions with more than one argument can also be defined using pattern matching, in which case the patterns for each argument are matched in order within each equation. For example, the library operator and logical and, that returns the conjunction of two logical values can be defined as follows. Okay, let's try that. Oh my God. Okay. So, for example, the library operator, how do you define infix functions? I don't know. Let's call it and b boolean. A b is a and then b. Let's just try that first. No. Okay, maybe it just works like this. A and B. No. I don't know. Let's see. Nope. Let's check it out. How to define infix function Haskell. There's no way to define a function with an alphanumeric name as infix. I did not ask that. How to define infix function Haskell? Infix function in Haskell. Okay. Oh my god. Oh, so it is with the backticks apparently, but you have to put it in between. Oh. Oh my god. I think this might be the worst episode so far. Why? Oh my god. Why is it selecting everything? Okay, there we go. Oh my fucking god. It fucking pasted that whole other buffer in here? A... and B is A N and B. True. Is it with the capital in? Yeah, I think so. True and B false. Nope. That doesn't work. Wow, this is annoying. Maybe it's... No, I'm pretty sure it's backticks, but... Oh, what? Is it impossible to define your own... Oh, maybe I have to write the type above it or something? What is it doing now? Oh my god. Okay, A and B is A and B and up, and B goes from bool to bool to bool. Ah, no. Nope. Okay, well, anyways, we can just define it as a normal function instead of a instead of an infix function, because I don't know how to do that. And be true, false. Okay. And now we can define it as and be of true, of false, and anything is false, and be of anything. I mean, of some Boolean b. Wait, of true and b is b. Oh. And be true, false. Okay, I think that's what they wanted to teach us. However, this definition can be simplified by combining the last three equations into a single equation that returns false independent of the values of the other two arguments using the wildcard pattern. What? What are they? They're defining a function with three arguments? Functions with more than one argument can also be defined using pattern matching, in which case the patterns for each argument are matched in the order within each equation. For example, the library operator AND that returns the conjunction of two logical values can define as follows. However, this definition can be simplified by combining the last three equations into a single equation that returns false, independent of the values of the two arguments, using the wildcard pattern underscore that matches any value. This version can okay, so and b of true and true is true, and b of anything else is false. That's pretty cool. This version also has the benefit that under lazy evaluation, as discussed in chapter 15, if the first argument is false, then the result false is returned without the need to evaluate the second argument. In practice, the prelude defines AND using equations that have this same property, but make the choice about which equation applies using the value of the first argument only. True and b is b. Oh, what? So you, okay. Oh my fucking. Okay, let's try it one last time to make this an infix function. No, that doesn't work. Okay. What if we just do this? Nope. That is blah blah blah. Note that Haskell does not permit the same name to be used for more than one argument in a single equation. For example, the following definition for the operator AND is based upon the observation that if the two logical arguments are equal, then the result is the same value. Otherwise, the result is false, but is invalid because of the naming requirement. B and B is B, underscore underscore is false. If desired, however, a valid version of this definition can be obtained by using a guard to decide if the two arguments are equal. So far, we have only considered basic patterns that are either values, variables, or the wildcard pattern. In the remainder of this section, we introduce two useful ways to build larger patterns by combining smaller patterns. Tuple patterns. A tuple of patterns is itself a pattern, which matches any tuple of the same arity whose components all match the corresponding patterns in order. For example, the library functions first and second that respectively select the first and second component of a pair are defined as follows. Okay. List patterns. Similarly, a list of patterns is itself a pattern which matches any list of the same length whose elements all match the corresponding patterns in order. For example, a function test that decides if a list contains precisely 3 characters beginning with the letter A can be defined as follows. Precisely 3 characters beginning with the letter A. Okay. Let's try defining that. Test of anything is true, is false. Yeah, let's try that. Oh. Okay, I don't understand. Maybe it has to be in double quotes or something. Oh no, okay, this is a list of characters, right? It's not a list of strings, so it has to be like this. Okay, test of B, C, D is false, false. That's cool. Up to this point, we have viewed lists as a primitive notion in Haskell. In fact, they are not primitive as such, but are constructed one element at a time, starting from the empty list using the operator colon called cons that constructs a new list by presenting a new element to the start of an existing list. For example, the list 1, 2, 3 can be decomposed as follows. Oh my god. No. Wow. I thought you could write it like this. Oh, yeah, they're gonna explain something. As well as being used to construct lists, the cons operator can also be used to construct patterns, which match any non-empty list whose first and remaining elements match the corresponding patterns in order. For example, we can now define a more general version of the function test that decides if a list containing any number of characters begins with the letter A. test2 Similarly, the library functions head and tail that respectively select and remove the first element of a non-empty list are defined as follows. Wow. Note that cons patterns must be parenthesized because function application has higher priority than all other operators in the language. For example, the definition head cons underscore equals x without parentheses means head x cons underscore, which is both the incorrect meaning and an invalid definition. 5.4 Lambda expressions. As an alternative to defining functions using equations, functions can also be constructed using lambda expressions, which comprise a pattern for each of the arguments, a body that specifies how the result can be calculated in terms of the arguments, but do not give a name for the function itself. In other words, lambda expressions are nameless functions. For example, the nameless function that takes a singular number x as its argument and produces a result x plus x can be constructed as follows. The symbol / represents the Greek letter lambda, written as lambda. Despite the fact that they have no names, functions constructed using lambda expressions can be used in the same way as any other functions. For example, lambda x goes to x plus x of 2 is 4. As well as being interesting in their own right, lambda expressions have a number of practical applications. First of all, they can be used to formalize the meaning of queried function definitions. For example, the definition add from int to int to int, add xy is x plus y can be understood as meaning and blah blah blah, yeah, which makes precise that add is a function that takes an integer x and returns a function which in turn takes another integer y and returns the result x plus y. Moreover, rewriting the original definition in this manner also has the benefit that the type for the function and the manner in which it is defined now have the same syntactic form, namely question mark goes to question mark. Secondly, lambda expressions are also useful when defining functions that return functions as results by their very nature, rather than as a consequence of querying. For example, the library function const that returns a constant function that always produces a given value can be defined as follows. Const a to b to a, const x underscore is x. What? Okay. However, it is more appealing to define const. Okay, yeah, I think I get it. In a way that makes explicit that it returns a function as its result by including parentheses in the type and using a lambda expression in the definition itself. Finally, lambda expressions can be used to avoid having to name a function that is only referenced once in a program. For example, a function odds that returns the first n odd integers can be defined as follows. I think the where syntax in Haskell is kind of strange, but whatever. The library function map applies a function to all elements of a list. However, because the locally, isn't that spelled wrong? I'm not sure. Because the locally defined function f is only referenced once, the definition for odds can be simplified using a lambda expression. 4.6 Operator sections. Functions such as plus that are written between their two arguments are called operators. That's why I couldn't find it on Google, because Haskell calls them operators instead of infix functions. As we have already seen, any function with two arguments can be converted into an operator by enclosing the name of the function in single quotes, as in 7div2. However, the converse is also possible. In particular, any operator can be converted into a curried function that is written before its arguments by enclosing the name of the operator in parentheses, as in parentheses plus 1, 2. Moreover, this convention also allows one of the arguments to be included in the parentheses if desired, as in 1 plus 2 and plus 2, 1. In general, if hashtag is an operator, then expressions of the form parentheses hashtag and x hashtag parentheses and parentheses hashtag, yeah, you can read it, for arguments x and y are called sections, whose meaning as functions can be formalized using lambda expressions as follows. Okay, so let's try for one final time to define an infix true. Wait. Abs to, no, what was I? And b of true and anything b is b and b of false and anything is false. No. True and be false. Nope. Why is this so difficult? Oh, maybe, okay, let's call it and see. True and C false. Nope. Okay, whatever. Functions such as plus that are written between their two arguments are called operators. Okay, yeah, we just read that. Sections as follows. Sections have three primary applications. First of all, they can be used to construct a number of simple but powerful functions in a particularly compact way, as shown in the following examples. Plus is the addition function. 1 plus is the successor function. Reciprocal, doubling, halving. Secondly, sections. Secondly, sections are necessary when stating the type of operators, because an operator itself is not a valid expression in Haskell. For example, the type of the addition operator plus for integers is stated as follows. Finally, sections. Okay, wait. Oh. Bool to bool to bool. Nope. Wait, how do you... Yeah, I really don't understand. Finally, sections are also necessary when using operators as arguments to other functions. For example, the library function sum that calculates the sum of a list of integers can be defined by using the plus operator as an argument to the library function fold L, which is itself discussed in chapter 7. What a bad example. Because we haven't even seen folds yet. 4.7 Chapter Remarks. A formal meaning for pattern matching by translation using more primitive features of the language is given in the Haskell report. The Greek letter lambda used when defining nameless functions comes from the lambda calculus. Exercises. Using library functions, define a function have that takes a list of a's and goes A to A that splits an even lengthed list into two halves. For example, ooh. So do they expect us to embed the fact that the function only works on even lists in the type? Because I don't know how to do that. Okay, have of. Oh, how are we going to do this? We can do it with we get the length and then we take and drop the half, the length divided by 2. But I was thinking, can you, yeah, no. I was thinking if you could match on the last element of the list, you could write a recursive function that conses to a pair, and then it conses the head to the first and the reverse head to the back of the second of the result, second argument of the result. But I don't, maybe we could do that. But let's try the easier one first. Have of x's equals, okay, how does that work? Can you do like this? Is it called len? Or is it called length? Nope. Length. Okay, have x's is defined as up. Is it take length x's divided by 2 x's. Maybe we should define this in like separate functions. Or yeah, let's do this in middle and drop middle x's where middle is div 2, something like that. Nope. How did he he did give an example where he does the where thing, right? Yeah, maybe the problem is, oops. Nope. We will, oops. Have. Nope. Oh yeah, what have I done there? It's strange that that compiled. What? Huh? What the hell is it doing now? Oops. Huh? What the hell? Yeah, why did I put commas here? I think I need to sleep. Yeah. Okay, so that kind of works. I wonder why he put that in this chapter though, because we didn't use guards or pattern matching. Okay. Exercise 2. Define a function third that takes a list of A's and goes to A that returns the third element in a list that contains at least this many elements using head and tail, list indexing, bang bang, pattern matching. Okay. Okay, let's do third one. Using head and tail. Okay, so third one, X's is head of tail of tail of tail of X's. Oh. One too many tails. So that works. Then third two x's is x is 3. Or is it 2 then? 2, I think. Third 2. Yes. I did not finish typing Haskell. Then, third of 3 of x's. Pattern matching. Okay. Then we do it like this. Nope. 1, 2, 3. Maybe no, I don't think that's gonna work. Oops. Yeah, no, that's wrong. I mean, we can do it with that ugly cons syntax, like this, right? No, like this. 1, 2. Then we want 3. Oh wait. Up, and then whatever else. Oh. Okay. Exercise 3. Consider a function savetail that behaves in the same way as tail, except that it maps the empty list to itself rather than producing an error. Using tail and the function null goes from that decides if a list is empty or not. Define savetail using. Savetail 1 of x's is equal to if null, is it with the question mark? Where is the no? If null x's, then empty list, else tail x's. Savetail 1, 1, 2, 3. Savetail 1. Boom. Now, savetail 1 of x's. Null x's is anything else is that, and this should be savetail 2. Savetail 2 of this, savetail 2 of 1, 2, 3. Oopa. Savetail 3 of x's. Pattern matching. Okay, savetail of the empty list is the empty list. Savetail tail 3 x's is tail x's. Oops. Save tail 3, save tail 3. Bam. 4. In a similar way to AND, in section 4.4, show how the disjunction operator OR can be defined in 4 different ways using pattern matching. I'll figure that one out when I know how to define an operator. Exercise 5. Without using any other library functions or operators, show how the meaning of the following pattern matching function definition for logical conjunction AND can be formalized using conditional expressions. Okay, we can't see that image. I think I've made a video for an hour, so I'm just going to end it here.